Well, welcome back. Everyone in the room has just had a bit of a break. Maybe you took a break too if you're watching online. Good. End of break, back to calculus. And today I'd like to talk about inverse functions. We said a little bit about this before, but I really want to concentrate on how inverse functions and calculus work together. Then I better do a survey of inverse trig functions because those are pretty important. We've actually seen perhaps the most important inverse function, which is log, the inverse of e to the x. Or vice versa. Maybe you think of e to the x as the inverse of log. But in any case, the inverse trig functions are pretty important, so we'll talk about them too. And then I want to jump ahead a little bit, at least as far as my book is concerned, to linearization. That goes all the way up to chapter 13, in fact, section 13.2. That's where it comes in the syllabus at Princeton, so that is where I'm going to cover it. But rest assured, I'm going to go back and cover everything else. So hopefully nothing will be missed. So any questions from anyone in here before I talk about inverse functions? Well, you know the drill. Ask questions anytime. We'll do homework problems at 9:30 after the video is finished. But if you have questions about what I'm saying, please don't hesitate to ask. I'm sorry? Okay, no problem set. When is it due? Next Wednesday. Okay. Right, so inverse functions. As I said, I already talked about this in the pre-calc section. Now we've got to do some calculus. But first of all, we better remind ourselves what an inverse function is. Just, if you write that y is f inverse of x, the most useful thing I can tell you about this is that you can then change this around and that write x is equal to f of y. If there is an inverse function for f, so if you can write this, then you can turn it around, move the f onto the other side so that x equals f of y. That's really, really useful to know. And it allows us to do quite a lot, actually. Anyway, question is, though, how do you even get an inverse function in the first place? How do you know that a function has an inverse in particular? And we did discuss this. There's this horizontal line test. This function does not have an inverse because it fails the horizontal line test. What does the horizontal line test even mean? Well, it means there are at least 2 points. Here there's one more. But there are at least 2 points that are at the same height. The function is at the same height above the axis. And so actually, whatever this height is, from here it would be f of a. But from here it would also be f of b. So actually, no inverse if f of a equals f of b for any two numbers a and b in the domain, as long as a not equal to b. No fair making them the same number. Then, of course, f of a equals f of b. But there's no inverse. That's the horizontal line test in math symbols. Now, it's amazing how few functions actually satisfy that. For example, if f of x is, say, e to the minus x squared, that's actually a bell-shaped curve if you were to plot it. And you can see that it fails the horizontal line test. But how do you know that if you don't know what the graph of this thing looks like? Well, what you could try to do is find two different numbers such that when you plug them in, you get the same answer. If you think about it, x squared doesn't care whether x is positive or negative. So, for example, f of 3 is e to the minus 3 squared, which is e to the minus 9, and f of minus 3 is e to the minus 3 squared, which again is e to the minus 9, e to the negative 9. And actually that's enough to show that it does not have an inverse. F has no inverse. You only need two pairs, in 2 points really, one One pair of points, 2 points, to shoot the whole thing down. It's very sensitive, this inverse business. Just show it one pair, 2 points that violate it, and it will fall over and there's no inverse. Okay? So in fact, if any function is even, then it can't have an inverse. No even function can have an inverse because f of x equals f of minus x. You can just pick any points like 3 and minus 3. This is an even function. It doesn't have an inverse. Okay, so that's the basic idea. So if you want the horizontal line test to work and your function is differentiable, meaning, remember that it's smooth, it has tangent lines, it can't look like this. One thing you could do is you could throw a whole bunch of this function away. For example, if you threw away this and just started it here, or any point to the right, that function with the restricted domain, as in this part, that's okay. So when is a function okay? Well, basically, I'm going to come out and state the result. Well, actually, no, I changed my mind. I'm going to provide a little bit of motivation. Here's a function that clearly satisfies the horizontal line test. Okay, and the interesting thing about it is that it is increasing. It's always getting bigger. It's getting bigger. So it doesn't have the chance to turn around and come down like this one does. This one is getting bigger here, then getting smaller, and then getting bigger again. But if it's all in one direction, there's an inverse. Now, of course, it could be getting smaller. That's okay. If it's always getting smaller, no problem. Okay, so this is going to be called increasing. This is decreasing. Okay, these are terms. Now, what if the function is momentarily flat? Something like this. So the tangent is horizontal there. It's still increasing. Even though it sort of levels off, there's no problem with the horizontal line test. The only problem could be this line, but sure enough, it still only intersects the curve at one point. So there's no problem if the curve is flat. What if it's flat for a little while? I could stitch together a curve like this, which has a constant piece. So this is supposed to be a flat piece. So this would be some piecewise defined curve with a flat section in the middle. Now that fails the horizontal line test pretty badly. In fact, that horizontal line, that one line there, intersects the curve not just twice, but infinitely many times. So that's got to be prescribed. So here are basically the rules. If any of these are true, well, actually I should add one little caveat before I launch into this. If f is differentiable, so you have some function, if it's differentiable on some interval ab, no fair breaking the differentiation somewhere in the middle, and then starting again. That's a function that's always increasing. Right? It's getting bigger, 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 bigger. It still doesn't have an inverse because we broke it. It has to be differentiable on the entire interval. So if f is differentiable on an entire interval and any of these are true, and I'm going to give you 4 things that are quite similar. They're quite similar. One is that the derivative is always positive. So for all x in the interval. So if the derivative is always positive, you should think of this curve as increasing. Always increasing. So that's good. Another possibility, let's see, is this the same order I do? Yes, I want to be consistent. If it's always decreasing. Decreasing. Another possibility that's good, and it's a little more complicated, but if it's always increasing and maybe equal to 0 somewhere, But it's only equal to 0 a few times, a finite number of times. So I'm trying to avoid this situation here, where it's infinitely often 0. Everywhere in here, the derivative is 0. And of course, I have to allow for the decreasing case. So this is also increasing with momentary flat points, and this is decreasing with momentary flat points. If any of these are true, then f has an inverse. Or at least f has an inverse on AB. I should say on its domain. Now, if its domain happens to be a closed interval, AB closed at the end, then this is still true. You don't have to worry about the derivatives on the end points. They can't really hurt you. Okay, so basically, if you want to show that a function has an inverse, you either have to show, so maybe we can look up here, you either have to show that for every single pair of numbers that you can possibly think of, meaning that you need to make them variables and let them be arbitrary, but for every pair of numbers, you do not have f of a equals f of b. And that can be quite tricky. The other option is to use a little bit of calculus. So I'd like to give you an example, and we're going to become quite friendly with this example. Suppose f of x is this cubic, 1/3 x cubed minus x squared plus 5x minus 11. So I'm sort of working in 10.1.1 in my book, but I've already talked about 10.1.2, so all that's left is to cover this example. Okay, so suppose f is this function, but I'm going to tell you, actually, what am I going to tell you? I'm not going to tell you anything. I'm just going to say the domain is all of R. The domain is the whole real line. So prove that f has an inverse. How are we going to do that? Well, we take the derivative. Well, what do we get? X squared minus 2x plus 5. All right, so we have this derivative. What are we trying to show? Well, according to what I wrote up, we'd like to show that the derivative is either always positive or always negative. Okay? How do you, first of all, do we think this is always positive? Always negative? Question.
We're trying to show that it's either always positive or always negative.
Right, so
or it's something equals 0, right?
The question is, of course, show f has an inverse. And there's many ways you could do it. But, as you say, a good way to do it is to show that the derivative is either always positive or always negative. Or maybe it can be 0, but only occasionally. Right?
So can you tell us how to do that?
I will. It is my full intent. In fact, this is a quadratic. And remember, quadratics either have 0 solutions, 1 solution, or 2 solutions. How do you tell which? Does anyone remember the word that I'm looking for? Discriminant. Okay. B squared minus 4ac, which people often write as delta. That's not the same as delta x. It's not changing. It's just the Greek letter delta for discriminant. Remember, if this is negative, no solutions to quadratic, as in the quadratic has no solutions. So in this case, the discriminant is minus 2 all squared minus 4, 1, 5. So that's 4 minus 20, negative 16, which is less than 0. So this means that this quadratic does not cross the x-axis. Whatever its graph looks like, it must be either always above or always below the x-axis. In fact, it must be always above, because if you put x equals 0, you get 5. Okay, so this shows that f prime of x is in fact greater than 0 for all x. That's one way to show this. Perhaps a better way, even, is to complete the square in the original. If you just complete the square like this, what do we actually want this to be? X squared minus 2x plus 1. Of course, then there's an extra 4 left over. And if you write it in this form, remember this is the derivative of the original function. If you write it in this form, you see that it's 4 plus something squared. So in fact, this must be at least 4, which of course is positive. And that's true for all x. So we have shown that the derivative is positive for all x. Therefore, f has an inverse. Okay? It's a sort of weird thing, but it's actually often easy to check that a function is always positive or negative. As you see, a good way of doing it is to show that that function has no intercepts. Of course, if that function isn't continuous, then it could kind of jump from one to the other, but this is a pretty rare thing. Normally, this sort of argument works well. Okay, are there any questions about that example? Sure. Yes? Well, what I want to do, so the whole aim of the game here is to show that f has an inverse, right? So what I want to do is, one way of doing it is to show that its derivative is always positive or always negative. Because if it's always positive, it's always getting bigger, no curving back upon itself and violating the horizontal line test. Okay? So how do you show that it's always getting bigger? Well, the derivative has to be positive. See, if the derivative's positive, then the curve is always getting bigger. Actually, I'm going to prove that I'm going to at least justify that statement next time after we do the mean value theorem. But until then, you're just going to have to sort of intuitively think that if the slope is positive, then it's always getting bigger. It makes sense. So what I have is I have to show this quadratic is always above the x-axis. So it's always positive, or always below the x-axis. And if you have a quadratic, the way to do that is to show that its discriminant is negative. If the discriminant is negative, there's no solutions, which means that the quadratic must either be above the x-axis or below the x-axis. If it crossed the x-axis, there would be at least one solution. Now, as it turns out, it would be okay if the discriminant actually equaled 0, because then the derivative would look like this, something like this. There would just be one point where it was 0. And as I said over here, it's okay if the derivative is always positive and sometimes 0, provided that it's only occasionally 0. It can't be 0 on a whole long segment like this, because that screws you up. Okay? Any other questions? Okay, well, there's a nice little tool to see whether a function has an inverse. Okay, and we've used some calculus to do it. Derivatives. So there's the first little calculus and inverses. Now, suppose that there is an inverse. So we have a function, and you know it has an inverse, either by this method or any other method you choose. So suppose that you start off with y is f inverse of x. So you started off with some function f. It has an inverse. The inverse function is f inverse, f minus 1. This is not the reciprocal, remember. That is the inverse function. So you say y equals f inverse x. What is dy dx? That is, what is the derivative of the inverse function? Okay, so obviously it's going to involve the derivative of f in it, but we somehow want to find the derivative of f inverse in terms of the derivative of f. And, we'll do an example of, say, inverse sine. inverse sine. We know what the derivative of sine is. What's the derivative of inverse sine? That's the motivation for this sort of question. So if y is f inverse of x, what is the derivative? And it's actually quite straightforward to do. We switch it around and start off, actually I'll work over here for a little bit more room. We start off with f of y equals x. See, if y equals f inverse of x, then f of y equals x. That's actually the first thing I said. You'll find it on that board up there, right on the top line. But we don't need to move the camera, because there it is again. If y is f inverse of x, then f of y equals x. Okay, you can flip the f onto the other side. So let's differentiate implicitly with respect to x. If you do that, the derivative of f of y is, of course, f prime of y. But you need to multiply by dy dx if you're going to do it properly. There's the chain rule. And on the right-hand side, the derivative of x is just 1. So we can rearrange, and you get that dy dx is 1 over f prime of y. And maybe I'll summarize it. If y equals f inverse of x, dy dx is 1 over f prime of y. So actually, derivatives have a reciprocal. Even though I caution, this does not mean the power minus 1. That's an inverse. Funnily enough, when you take the derivatives, you kind of got the reciprocal in there. Although it is f prime of y, not f prime of x. And that is a common source of error. In fact, to show you what the full formula is like, let's take this and repeat if y is f inverse of x, dy dx equals 1 over f prime of y. But instead of y, right, here's the y down there. What is y? Y is f inverse of x. So I'm going to change the y to an f inverse of x to produce this rather startling or bizarre looking formula. Dy dx is 1 over f prime of f inverse of x. It's pretty mean, pretty messy, but that's what it looks like. Okay? What we're doing is we're differentiating f, and then we're evaluating it at the point f inverse of x, not at x. Okay? Both these formulas are true. They both work. It's just this has a y on the right-hand side, and here I've eliminated the y. Okay, so I'd like to give you some examples of how to use this. Suppose, so the first one's fairly straightforward. Suppose that f of x is 1/3 x squared, x cubed, rather, minus x squared plus 5x minus 11. That's the same function that we looked at before, and we proved that it has an inverse. Okay? So the question is, so part A, if y is now the inverse function of f, evaluated at x, what is dy dx? And the second question is, find f inverse prime at minus 11. Okay. Get myself a little bit of real estate here on the board. Anyone have any questions while I'm doing this? If you do, start calling it out. All right. Okay, well, we better solve this problem. Now, before we actually even commence with the solution, I want to point out something. We had f of x equals this, and now we've got f inverse of x, and they are different functions. We must not think of them as the same function. Okay? Anyway, we can try to apply our formula. What we're trying to do is we're trying to find dy dx. So according to the formula in the box, this is 1 over f prime of y. Now what is y? Y is in f inverse of x. But I got to remind myself what f is because I can't see all the way over there. So for the third time, I'm going to write out this silly old function. Minus 11. Well, we're going to need f prime. So again, it's the same as what we had before. So actually, according to that derivative formula, it's 1 over y squared minus 2y plus 5. The problem is, we don't know what y is, right? How do you actually find the inverse function? Well, if you think about it, we're trying to find y equals f inverse of x. So this means that x equals f of y, and f of y is just this formula, but with x replaced by y. And so all we've really done is switch x and y in the formula y equals f of x. And you knew this rule before, of course, that to find the inverse function, you switch f and y. The problem is, if you actually want to find what y is in terms of x, you have to solve for y. Oops, how did that x get over there? Sorry, it's a y. So you have to solve this for y, and we don't know how to solve cubics like this. So actually, the best you can do is leave this answer in this form, where y solves the equation x equals 1/3 y cubed minus y squared plus 5y minus 11. So it's sort of oddly unsatisfactory, but that's the best you can do. If you like, you could replace y by f inverse of x, but you can't easily find that in terms of x. However, you sometimes can in specific cases. So for example, we are trying to find, by the way, for part B, before we even begin, I want to point out that this is exactly the same thing as the derivative of the inverse function. Right? Because y is indeed the inverse function. So this is the derivative of the inverse function. So for the second part of the problem, we need f inverse the derivative at minus 11. So that means we have to set x is minus 11, and then we have to find out what is y. Well, we can use this equation here. If x is minus 11, then we have minus 11 equals 1/3 y cubed minus y squared plus 5y minus 11. And we're actually quite lucky because we can cancel out the 11s, leaving a 0. And now we can actually factor the right-hand side. The right-hand side is 1/3, well, it's actually y outside of 1/3 y squared, minus y plus 5. And that has to equal 0. Okay? Y could be equal to 0 here. And then we'd have a solution. Maybe that quadratic has a solution. Who thinks that that quadratic has a solution? Who thinks it doesn't have a solution? Who doesn't think? Good. Okay. And of course, you know, you might have known the answer if you're watching there, but I can't hear you, so I'll just give you the benefit of the doubt. Actually, you could check the discriminant. It's going to be 1 minus 4/3 times 5. It looks pretty negative to me, but even without checking it, this can only have one solution. If this had multiple solutions, there would be no inverse. Right? The whole idea of the inverse function, if it exists, is you switch x and y, and you hope there's only one solution. If you solve for y, there cannot be multiple solutions. So, in fact, I would have been flabbergasted if there was a solution, because that would mean 0 and something else would solve the equation. And so the horizontal line test would be violated for minus 11. Anyway, so the solution can only be y equals 0. Okay, so when x is... So we've actually proved that the inverse function at minus 11 is 0. Or if you prefer, when x equals minus 11, y equals 0. Bearing in mind, of course, that y is the inverse function of x. Just remind you, these two things mean the same thing. And we need to find the derivative. Well, we know that the derivative actually, that's not the way I want to write it. It's the bad way to write it. It's the inverse function derivative. We have proved above in part A that this is 1 over y squared minus 2y plus 5. So when x equals minus 11, y equals 0, and we just plug everything in, and we get 1 over 0 squared minus 2 plus 5, which is 1/5. And that's the answer. Okay, the great temptation is to take this formula and put minus 11 into it. But that is wrong. You have to put 0 into it, because f inverse of minus 11 is 0. And this is a y, not an x. So if you keep your y's and your x's sorted out, always keep reminding yourself that y equals f inverse of x. Then you should be able to get this thing the right way around. The confusing thing, of course, if I may just come back up here, is that you have to take this equation. The best thing to do is to write that equation first. Because you see, the original up here has an x there, and you need to originally swap x and y around to get the inverse. So you're dealing with inverses. The first thing you have to do is swap x and y, and that's the equation that matters. That's the equation. The first equation with the x's is just f of x. We're concerned about f inverse. Okay, so to review the steps then, basically, you start off with any function y equals, well, you start off with f of x, but then you write down y as f inverse of x, switch the x's and y's like this, so that you know what's going on. Then the derivative is 1 over the derivative of the original function, but with a y instead of x. Okay? And then, if you actually have to find it out at a particular place, plug in your value of x into your equation, find the right value of y, and then plug that in. So you have to dance around a little bit. It's not just plugging in x's. You've got to sort of use the original formula, get the y, and then plug that into the derivative formula. Okay? It's quite confusing. It's quite confusing. And kind of got to wrap your mind around it. Not so easy. But it's just practice. Anyway, I'm going to do some more examples. First, I need some more board. In which case, I need to know if there are any other questions. If you have one, ask and I shall listen. If not, well, you know, you get the same answer. They're the same. Sorry, who asked the question? Yeah, the formula is basically the same. It's just, it's really one formula. So if you do use f inverse, you still cannot find a good expression for f inverse. So there's no other real... The two formulas look different, but they're just the same formula. So I'm afraid they inspire the same method. The only other thing you could possibly do is to solve, switch x and y and then solve for y. If you actually can find y in terms of x, then you can differentiate dy dx, and that's it. And then you'll get an answer in terms of x. But you see, in that case, if you can actually find the inverse function, of course you can differentiate it. The problem is, what if you can't find the inverse function, like in that case? Then you have to do that sort of rigmarole to find it. But The nice thing is you can get the derivative even if you don't know the derivative, even if you don't know the inverse function everywhere. If you know it at one point, then you can find at least the derivative at that point. And here's another example that's more abstract. Suppose g of x is sine of f inverse of x, where I'm not going to tell you much about f. I'm only going to tell you a couple of things. All we know is that f of pi is equal to 2 and f prime of pi is equal to 5. So f is a differentiable function, and I'm assuming that it's invertible. So let's say its derivative is always positive. I don't know. This would all be part of the question. I'm just too lazy to write it down. So f is some function. It's differentiable. In fact, its derivative is always positive. And so it has an inverse, f inverse. And all we know about f, the original function, is that f of pi is 2. And f prime of pi, the derivative evaluated at pi, is 5. And so the question is, what is the question? Show g of 2 equals 0 and find g prime of 2. That's the question. So it's not like you can possibly draw a graph of g, since we really know almost nothing about f. We know next to nothing about f. So how on earth can we find anything about g? Well, actually, I'm not asking you for much about g. I'm certainly not asking you for what the derivative is at any particular point, just at 2. Okay? So anyway. Well, let's just do the first part. G of 2, we take the original formula for g, and we plug in 2. So it's sine f inverse of 2. Question is, what is f inverse of 2? Well, take this equation and flip it around. F inverse of 2 is pi. So if f of pi is 2, then f inverse of 2 is pi. So this means that this quantity here is just sine of pi. But of course, sine pi equals 0. Sine of... Sure. Sure, I'll work through all the steps. I started off with g of x is sine f inverse of x, right? The original function. I need to show that g of 2 is 0. So I start off with g of 2. I take the original function, and I replace x by 2. Okay, so I just need to find what f inverse of 2 is, right? So in order to do that, I notice that f of pi equals 2, and I can flip that around, put the f on the other side as an inverse. And so f inverse of 2 equals pi. So now I plug that value in here, and I have sine pi, which is just 0. Okay, so actually that's not even calculus, that's just sort of inverse functions. Now we even have to do some calculus. Now, this is where you better whip out the formula. I'm going to rewrite g of x, just because it's all the way up there. What should the derivative of g be? Well, we have to use a rule. Can anyone shout out what rule it is? The chain rule. We're dealing with a composition. It's sine of f inverse of x. So what's the derivative of sine of something? Cosine of that something. But then you have to compensate for the fact that the something isn't just x by multiplying by the derivative of it. If you prefer, you can let this be y. I'll show you. Actually, you know what? I think that computation is even easier. I can show it to you in parallel, and it doesn't matter. Let y equal f inverse of x. So g of x is actually equal to sine of y. So g prime of x is cosine of y dy dx. And of course, y is the inverse, and we know from our formula before that dy dx is 1 over f prime of y. That was the first formula that I wrote. If y is f inverse of x, dy dx is 1 over the derivative at y. So if g of x is sine of y, g prime of x is cosine y dy dx, which is cosine y times 1 over f prime of y. So that is what you get using this y notation. Actually, if you come over here and follow what I was about to do, we can use the other formula that I wrote up before for the derivative of the inverse as f prime evaluated at f inverse of x. Okay, these are two parallel lines of argument, but they're actually exactly the same. The only difference is here I don't have any y's, and here I have y's. In fact, if you look at the final answer and you change y to f inverse of x, you will get this formula. There's one y, there's another y. So it's up to you which method you prefer. But in the end, you kind of need this formula here. You see, we need to find what g prime of 2 is. According to this is cosine of f inverse of 2 times 1 over f prime at f inverse of 2. Now we have to start using our data. I just want you to understand, we took g, we used the chain rule on it, and we used the rule I put up in a box earlier. Then I've just plugged in 2 because the problem asked what's g prime of 2. Well, we worked out what f inverse of 2 is. We've already seen that f inverse of 2 is pi. It's all the way up there. I don't know if you want to show it again. Just up there, f inverse of 2 is pi. So we now have to come back here and write this as cosine of pi times 1 over f prime of pi. Because we know f inverse of 2 equals pi. Well, cosine of pi is equal to minus 1, and f prime of pi was given in the question to be 5. So the answer is minus 1/5. That's pretty tricky. You may have to stare at that for some time. It is actually in the book in section something or other, 10.1.3. Section 10.1.3 of the book, that exact example. Now, the thing is, that's the purest way of doing it. If you want to come over here and do it in terms of y's, then you have to do a little bit extra work from the original. You have to start off with we've already said that y is f inverse of x. So we know that f of pi equals 2. So f inverse of 2 equals pi. And another way of saying that is you've got to say when x equals 2, y equals pi. If you do that, you can come back over here and say that g prime of 2 is equal to cosine of pi over 1 f prime of pi. And of course, you get exactly the same answer. Now, okay, so basically the two methods are the same. One introduces y as f inverse of x, and the other, this first method doesn't have any y's in it. It may not be wise to use the method without the y's. That's pretty bad pun. Okay, so anyway, but this may be an easier way if you prefer, because you just have to write down f inverse 2 equals pi. when x equals 2, y equals pi. So whenever you substitute in a formula like this, replace x by 2, you've got to replace y by pi. It's a sort of simultaneous substitution. These formulas have x on one side and y on the other. So you have to plug in the right value of x corresponding to the right value of y. Tricky stuff. I don't think this is a very easy problem. I've seen these sorts of things on Princeton exams before, and they're not normally done very well. So you'll have a bit of an advantage if you know how to do them. They're often worth quite a chunk of points, and they don't take very long to do if you know how. So I want to look at a big example that actually illustrates all these points, everything that I've said today almost. This is in section 10.1.4. After that, I'll move on to inverse trig functions. And then after that, linearization. So that's the game plan. Try to peer at that clock there. Okay, 10.1.4. Here is a nice function. F of x equals x squared, x minus 5 all cubed. So it's actually a fifth degree polynomial. But I'm going to restrict the domain to the interval 2 comma infinity, closed at 2. It can never be closed at infinity because infinity is not actually a number, so we can't include it. Okay, so here is a particularly, perfectly nice function. I don't know about particularly nice, but it's a reasonable function. And I would like to show 4 things about it. 1, show f has an inverse. 2, find the domain and range of the inverse function. 3, show f of 4 is minus 16. That one doesn't sound too bad. And finally, 4, find the derivative of the inverse function evaluated at negative 16. Okay, so there's a nice little problem that ties together all of these points. So, we better start with the first part. Okay, to show that f has an inverse, one thing you could do, of course, is show that f of x, or f of a equals f of b has no solutions. That is a pain. We're going to use our derivative test. We need to differentiate f of x. So f prime of x, unfortunately we have to use the product rule. So according to the product rule, it's v du dx plus u times the derivative of v. Well, the derivative of something cubed is 3 times that quantity squared. And when that quantity is as simple as x minus 5, then there's not even any derivative. You can multiply this by 1 if you like, since that's the derivative of x minus 5. Anyway, in order to deal with something like this, the best thing is to factor it. You'll notice that x is a factor, and actually x minus 5 all squared is a factor. And then what's left? Well, over here, you have twice x minus 5. And over here, you have a 3x. You believe that? X minus 5 all cubed, we have x minus 5 there and the coefficient of 2. Whereas here, we only have the square, but we have an x squared. So we have an x, 3x takes care of that coefficient. So now, actually, this gives us the complete factorization. 2x minus 5, well, that's 2x minus 10. And plus 3x, so it's going to be 5x minus 10. And actually, I'm going to pull out the 5. And you get this. 5x, x minus 5, x minus 2. X minus 5 all squared, rather. X minus 2. So that's the derivative. What do we want to show? I forget. I don't really forget, but I'm hoping that someone will tell me. It's always positive or it's always negative. Okay, but the domain is not all of the real line. In fact, it begins at 2 and goes to infinity. Now, you don't actually have to check 2 because it's an endpoint. I remember I said only the interior matters. So we have to say on to infinity, we want this to be always positive or always negative. So in order to do this, let's look at what happens, i.e. x greater than 2. So if x is greater than 2, tell me about 5. Positive or negative? Okay. Someone else tell me. If x is greater than 2, then is x positive or negative? Or could be either? Positive. How about x minus 5? Could be negative, but squared. Yes, squares are always positive. Could be 0, but not in this case, because, well, actually, it could be 0, and let's be careful here. This could be 0 when x equals 5. What about this term, when x is greater than 2? That's positive too. So this is positive, and this is positive or 0. So the conclusion is that this is actually greater than or equal to 0 when x is greater than 2, but it might equal 0. In fact, it only...
Can it also equal 0 in the right than x minus 2?
Well, when x equals 2, it equals 0. But remember, that's just an endpoint, and it doesn't actually matter. The endpoint does not matter, because there's only one point. And you cannot move from that point to another point that is on the same height unless you go up and then down in the meantime, in which case you would have to be up and down. There's no next point to be equal to, so there's no problem at the endpoint, as it turns out. So actually, it only equals 0 when x equals 5. So let's review the situation. We have this function. On its domain, not including the endpoint, at 2, it's always positive, at least the derivative is always positive. But there's one point where the derivative equals 0. That's okay. Remember I said it has to be always positive, but it's okay if 1 or 2 or 10, some finite number of points, the derivative is 0. So it's actually, the function must look something like this. It starts at some height at x equals 2. I don't know. We'd have to plug it in to see where. Actually, if you do plug it in, I believe it's minus 108. You have to plug it into the formula and see what you get. But it starts at that height. Actually, you know what? We're going to need to do this for part B anyway. So let me just solve part B, and then we'll see what the full situation is. So for part B, we need the domain and the range of f. We need the domain and the range. Okay, of f inverse. But let's just find the domain and range of f. Do f first. Well, we already know the domain of f. Right? They gave it to us in the question. I gave it to you. Whoever made up the question gave it. Actually, I made up the question. So I gave you the domain, and I said it was to infinity. So what does that tell you about the inverse function? That's the range of the inverse function. So the range of f inverse, so they swap domains and ranges. The domain of the inverse is the range of the original, and vice versa. Now, we need the range of f. Okay, now this is where I'm going to pull out a graph. I do not need to sketch this function, although I will use it probably as an example of curve sketching. What do I know? F of 2. Let's just find f of 2. 2 is at the very end point. If I actually plug it in, I get 2 squared times 2 minus 5 all cubed, which is 4 times minus 3 cubed. 4 times minus 27 is minus 108. You don't need a calculator to do that. It's easily enough done. Okay, so we know that the function starts here. Now, what else do we know about the function? It's always increasing, except maybe at 5. Actually, if you plug in 5 into the original thing, you get 0. So the function's got to look something like this. It increases, it's actually flat here, but just for a second, and then it keeps on going. The only question is, does it peter off into like a horizontal asymptote, or does it keep on going up forever? Well, if you take limit of f of x as x goes to infinity, this is just the limit of x squared times x minus 3 all cubed. That's what the function is. Oh, x minus 5 all cubed. My apologies. So when x gets really big, this gets really big, this gets really big, of course this limit is infinity. It's not even a poly over poly. There's nothing to do. It's just humongous. So actually, it keeps on going. It does not tail off. So my question for you is, what is the range of f? Negative 108 to infinity. Let's fill it in here. So this is domain of f inverse. And I'll erase some board while you're pondering that. So actually, the inverse function has domain minus 108 up to infinity, but the range is only from 2 to infinity, inclusive. Well, actually no. If the function had looked like this and had a horizontal asymptote, f prime would still always be positive in that picture at least. Right? It's always increasing. It starts increasing not very much as it gets to the asymptote, but it's still always getting closer, so it's always increasing. Right? You actually need the second derivative to tell whether it does that or whether it does that. Without doing some sort of limit thing like this or some other thing. And that's next week and the week after, that's where we look at that. But just because it's increasing, you don't know whether it does that. Or it could just be a 1. But any other questions? Actually, while I'm over here, I might as well plot what the inverse looks like. The inverse starts at minus 108, comma 2. This graph is not to scale because here's 2 and here's minus 108. So unfortunately, that is the case. But at 5, the tangent is actually horizontal here, so it will become vertical here. And what you'll find is that you get something like this. And so on. It's the reflection in that mirror. So if that's what the original function looks like, this one has to look something like this. And actually, eventually they will cross, and the original function goes up quite steeply, while the inverse function is more gentle, but it does not have an asymptote itself. It just keeps on going up fairly gently. So that's still down, but not as down as this. These limiting behaviors are quite tricky. Okay, well, we better do the third part. We are supposed to show f of 4 equals minus 16. Well, f of 4 is 4 squared times 4 minus 3 all cubed. Is that right? 4 minus 5 all cubed. I keep putting a 3 there. So that's 16 times minus 1 all cubed minus 16. Okay, that was sort of a bit of a walk in the park, but of course I'm setting up 4 where we want to find f inverse, the derivative of that at 16. Well, of course, if you whip out my formula, actually I didn't write it in this form. I put y's in it, but maybe I should have just written this. I did use this once. This is the completely y-free form. And I'm going to put a box around it. Just add that to the collection from before. That's, the first formula had all y's. The second formula, I removed the y on the right-hand side, but I did not remove it on the left-hand side. This just tells you, in pure function notation, what the derivative is. So in our particular case, we want the derivative at, question says, minus 16. So this is 1 over f prime f inverse minus 16. So this is what we want, and this is how we're going to get it. The question is, what is f inverse of minus 16? Well, where's minus 16 floating around? You see it? Yeah. See, from the third part, if f of 4 is minus 16, then f of minus 16 is 4. So this, of course, is 1 over f prime of 4. And we actually calculated what f prime is. If you come back over here, it's on that bottom line, 5x, x minus 5 all squared. And the last factor was x minus 2. So this is minus 1 all squared is 1. You get 5 times 4 times 2. 40. Let's see if I'm right. I don't know if I'm right. I didn't write it down. Actually, I'm not right because I forgot the reciprocal. Somehow, I magically put the denominator up as a numerator. Anyway, so that is the complete question. Anyone have any questions about it? It's kind of a showcase example for all the things that you might want to do with inverse functions, apart from inverse trig functions. So, if no questions, then, speaking of inverse trig functions, let me spend about, let's see if I can do it in 15 minutes. I just want to talk about inverse trig functions because they come up fairly often. We have to do a bit of calculus with them. I'll spend most of the time on inverse sine, then I'll repeat for inverse cosine and inverse tan and inverse secant quite quickly. So let's start off with sine x. So if you draw this beast, etc. Fails the horizontal line test pretty miserably, really. Any of these horizontal lines here between minus 1 and 1 actually intersect the curve infinitely many times. So clearly we have to do something, and it turns out that a pretty good thing to do, it's not the only choice, but if you throw this away and start here and stop here and throw all that away, you do get a function which is increasing all the time. In fact, the derivative of sine x is cosine x, and cosine x is actually positive in the fourth quadrant and the first quadrant. So, as it turns out, the derivative of this thing is always increasing, but you can actually see it from the graph, no big deal. The proof is using the derivative, but I think it's pretty clear. So if we restrict sine to between minus pi over 2 and pi over 2, then you do have an inverse function. And so there is an inverse sine, and the domain of this has got to be minus 1 to 1 inclusive, because that's the range of the original function. This function, we've thrown this away. In fact, I'm just going to gray it out because it's not really relevant anymore. What's going on here is that the original range is minus 1 to 1, so the domain of inverse sine becomes that. And the range of this is minus pi over 2 to pi over 2. That's the domain of the original function after we've restricted it. So the domain was minus pi over 2 to pi over 2. So the range of this becomes minus pi over 2 to pi over 2, and the graph looks something like this. Pi over 2 is a bit bigger than 1, so actually... Now, it's not flat here. In fact, it's supposed to have slope 1, so I didn't even draw it particularly well. It's not flat there, just as the original sine is not flat. If you have trouble remembering this, just mentally put in the rest of the sine curve like this. It can't actually be there, or else the vertical line test wouldn't work. Just like the horizontal one wouldn't have worked there. But nevertheless, there is the domain. There is the sketch or the graph of what this thing looks like. Okay, so we now know all about this. Now, the question is, what is its derivative? Actually, before we even do the derivative, does it look like an odd function, an even function, or neither? Just from the graph. It looks odd. In fact, sine is odd, so the inverse function has inherited that oddness. So this is odd. We need to differentiate it, and I can use the formula. Let y is equal inverse sine of x. So, dy dx, according to this, is equal to 1 over f prime of y. 1 over f prime of y. Well, f prime, what's f? If you look back over there, f of x equals sine x. So f prime of x is equal to cosine x. I'm leaving some room to state what the derivative is. F of x is sine x, f prime of x is cosine x. So the derivative is 1 over cosine of y. What's 1 over cosine of y? That can't be the derivative. We wanted something in terms of x. So let's draw a little triangle. If y is inverse sine x, then x is sine y. So that suggests that maybe we should draw a triangle here and say, okay, that angle is y, and sine of it is x over y. And so this side is 1 minus x squared, the square root, by Pythagoras' theorem. So actually, cosine of y is the adjacent over the hypotenuse. Which is, so cosine of y is just root 1 minus x squared. So we fill that in, and we found our derivative, which I'm now going to summarize over here as d dx of inverse sine of x is 1 over square root 1 minus x squared. And that will get an extra box around it because it is an addition to our list of derivatives. So we have differentiated inverse sine of x. It doesn't look anything like inverse cosine of x. In fact, it doesn't have any trig in it at all, which is kind of nice. Actually, the derivative of log x didn't have any e's in it. It was just 1 over x. So the derivative of inverse sine is just 1 over square root 1 minus x squared. Sort of surprising, but that's how it turns out. That is how it turns out. So this is just the cosine and the identity all sort of wrapped into one. Anyway, for all practical intents and purposes, you do not need to, at least at Princeton, I've never seen a reproduction of this proof, but plenty of times you'll have derivatives involving that. So you better make sure you can use the product rule and the chain rule and all that sort of stuff. In fact, maybe I'll whip out an example over here. Just need a little bit of space again. Any questions about anything I've said over there? If no one asks a question, then we'll either have silence or perhaps I will yodel. I thought that would actually precipitate a question. The yodeling would not have been pretty. Okay, so just a quick recapitulation, although, again, you don't technically need it for Princeton exams, but for your own understanding, if f of x is sine x, you agree the derivative is cosine. Okay, so if y is the inverse function, right, then we know that dy dx is 1 over f prime of y. That's the formula that I put up earlier. Okay, so that's 1 over cosine of y. And I would love to say d dx of inverse sine of x is 1 over cosine of y. That would be correct. But then y is equal to inverse sine x. So in some sense, this formula, let's see, I could have written 1 over cosine of inverse sine of x. That is also the correct formula. However, that looks really ugly. And if you use Pythagoras' theorem, you can actually show that that's the same thing as this. By doing, if x is sine y, then sine of y is x over 1. Take Pythagoras' theorem. And then cosine of y is just root 1 minus x squared. So I just plug that in. Kind of a nice little thing. If you actually want to avoid the formula altogether, you can just write x equals sine y and then differentiate it. That's in the book too. But I thought I might as well use the previous formula that I had developed. Anyway, now that we have this differentiation formula, just make sure you can differentiate things like this. This is a fairly straightforward example, but I just want to demonstrate you could use the chain rule to do it, or you could write the answer straight down. Right? Basically, the formula would have been 1 over root 1 minus x squared, but now we have 7x instead of x squared. Bang. But of course, when you replace x by a multiple of x, you have to multiply by that multiple. We saw that all the time. E to the 3x, the derivative is 3 e to the 3x. Here, it's a 7. So actually, you should clean this up to 7 over 1 minus 49x squared. And there's another example in the book about with product rules and stuff. This is the sort of thing that it's just an extra formula that you have to add, but all the rules still apply. The chain rule, the product rule, the quotient rule. Make sure you know how to use them. So that's just practice. Okay, so we better repeat the exercise really quickly for cosine, because I do need to talk about linearization. So, okay, here's the deal with cosine. Since it starts like this, you cannot go from minus pi over 2 to pi over 2. That actually fails the test. Instead, you go all the way up to pi. So actually the function's always decreasing. Its derivative is minus sine, which is positive in the first and the second quadrants. Well, the sine is, and minus sine is negative. So this function's always decreasing. And so that inspires an inverse function that looks like this. If you look at that, it's just cosine tipped on its side. But we've changed where we've restricted it. So in fact, for inverse cosine, the domain is again minus 1, 1, but this time the range is 0 to pi. It's a little bit different. It's not symmetric like the other one was, and it cannot be. It cannot be. Horizontal line test doesn't check out. So that's what the thing looks like. It's not an even function, even though cosine is even. Remember I said even functions don't actually have inverses. So we have to throw away the left part of it, and so a lot of the right part is no longer an even function, of course. So this is not an even function either. There's neither. And if you repeat the analysis, I'm not going to do it again. It's in the book, and I leave it as an exercise in any event. You can show that the derivative, a little bit surprisingly, is minus 1 over square root 1 minus x squared. So that should look pretty familiar. In fact, that is minus the derivative of inverse sine that we just found. Seems a little bit weird. But actually, if you draw inverse sine here, It's sort of the negative of this, but shifted up. The slopes are always the opposite. So they're really the same function. They're just flipped. Inverse cosine, inverse sine. I sort of flipped around this line, which is at pi over 4. There's a bit of a discussion of that in the book as well. I should probably say what section it is, just for reference. Oh, I guess it's in 10.2.3 or something like that. Might be 10.2.4. Okay, so that's inverse cosine. Let's quickly repeat the dose for inverse tan, because it's a little bit different, and that one is actually a pretty important function. Tan goes like this. So it has asymptotes every pi over 2, or actually every pi, centered at pi over 2, and it's, again, miserably failing the horizontal line test, so you have to throw most of it away. But you can keep one whole swoosh. Hope I'm not infringing any trademarks by drawing a swoosh. You can keep a whole thing like that between minus pi over 2 and pi over 2. You can tip it on its side and get the graph of inverse tan. It looks like this. It's not vertical here. It's actually slope 1 here, because the original is not vertical either. But it does have asymptotes. The vertical asymptotes of the original are now horizontal asymptotes. So basically the domain is all of R. It's the whole real line, because that's the range of the original function. The range is similar to the range of inverse sine, except instead of minus pi over 2 to pi over 2 inclusive, it's actually just open brackets, because they're asymptotes. It's also an odd function, as you can see from the graph. It inherited the oddness of the original. And also, we have two limits that are important. And they're based on the horizontal asymptotes. So the others do not have any asymptotes. But these you need to remember. I've seen them pop up in limit questions. I didn't really talk about them too much when I was doing the review of limits before. I mentioned them, but they do sometimes pop up. Sometimes they're just stuck on as a factor. You take any limit at infinity, or minus infinity, and whatever it was, it could be a poly over a poly, or one of these trig things, sandwich principle, who knows? And you just multiply that by inverse tan of x. And of course, the answer is the same, except multiplied by pi over 2. You just separate the product of the limits. It's the limit of the product, or rather the limit of the product is the product of the limits, etc., etc. The point is, know these formulas, because they do slip in from time to time. Now, we need the derivative, and again, it's the same sort of calculation. It's in the book, and you end up with this formula. Similar, but a little bit different. There's no square root, and there's no minus. It's a plus. And that is obviously going to be quite important. That derivative is going to pop up all the time. I should mention, which I should have mentioned before, that instead of inverse tan, you sometimes see arctan, arcsine, arccosine. ARC put in front of the trig function. That's the same thing, arctan. The reason people write arctan instead of inverse tan is actually because of the confusion. Does this mean 1 over tan x? Because, tan squared x is the square of tan x. Why isn't this the minus 1th power? It's just sucky notation. What can I say? It sucks, but that's what you got. So if some people write arc, I don't know, I was brought up on that, so that's what I write. I don't know. It's different. Every textbook's different. Well, not every textbook. Some textbooks are inverse tan. Some textbooks are arctan. And I guess it's conceivable you might see atan somewhere, just ATAN. But I haven't seen anything more exotic than that. Oh, I should do inverse secant, but I'm getting kind of bored of all these inverse functions. Maybe I'll just do it really, really, really quickly. bit of a weird function. Doesn't really come up much, and the other two almost never. They're cousins anyway. It's all in the book, but just for reference here, if I try to do inverse secant, without much ado, I've kind of got to restrict the original secant function the same as I did for cosine. I'm just going to restrict it from 0 to pi, but actually it's not even defined at pi over 2 because of the asymptote there. So if you draw the graph of this bizarre inverse function, it looks like this. It has a horizontal asymptote. There it is. Inverse secant x. Bizarre, but that's what it looks like. It is actually vertical up here. Because if we kept on going, it would turn around. Anyway, so let's see. The domain is actually, you can go up to -1, and you can go from 1, but you cannot go in between -1 and 1. Cosine, of course, is only between -1 and 1. Secant's, the reciprocal, is only outside -1 and 1, including the endpoints. The range is everything from 0 to pi, except not pi over 2. That actually omits. And we have a limit that I have actually never seen written down in a single Princeton exam, for what that's worth. Right? As you go up, you approach pi over 2, and actually the negative one is the same. It's not minus pi over 2. That would be a lovely trick question, but it's just so obscure and arcane that I can't imagine. I don't know. You could draw a graph and get it right, but I wouldn't know that off the top of my head. I have to draw a picture of it. So I haven't put a box around these. On the other hand, I have seen that the derivative comes up from obscure blue moon to blue moon. And it has a bit of an uncomfortable feature in that it has an absolute value. You sort of have to treat the left part and the right part separately because there's this whole gap in the middle. And if you don't have the absolute values, then this one looks like it's going down instead of up, and that's wrong. Anyway, so that's pretty obscure stuff. I would concentrate on inverse sine and inverse tan. Inverse cosine a little bit, but it doesn't come up very much because it's so similar to inverse sine. So inverse sine, inverse tan. Those are the two main ones. Okay? And you do have to be familiar with these functions. That's why I spent a few minutes on each one to make sure that you did know. I didn't do a lot of examples of differentiation, but I expect you to use those formulas to investigate. Now, I do not have time to do this. I'm probably just going to say a little bit of something. I want to just very briefly touch upon 10.2.6. But I advise you, if you really want to master inverse trig functions, to read this. It's got quite a lot of examples. But I just want to do one example of where inverse trig functions can really trip you up. I ask you this. What is inverse sine of sine 13 pi over 10? Well, the gut reaction is it's 13 pi over 10. But that cannot be, because if you take inverse sine of something, the range is minus pi over 2 to pi over 2. I wrote that up earlier. So the answer that you get by taking inverse sine of anything, I don't care what it is, if you're going to take inverse sine of anything, the answer's got to be between minus pi over 2 and pi over 2. Or maybe not defined, but it cannot be outside that interval. So when you take inverse sine of this, the answer cannot be 13 pi over 10, because 13 pi over 10 is bigger than pi over 2. So that cannot be right. What is the correct answer? Well, in order to really get it down, the best thing to do is to draw a picture of it. And 13 pi over 10 is a little bit bigger than pi. In fact, it's 3 pi over 10. So what I need to do is understand, first of all, is this positive or is it negative? So this is 13 pi over 10. So sine, we're in the third quadrant. Sine, positive or negative? Come on. ASTC. Negative. So actually, this is negative. Okay. What's the sine the same of? Well, the reference angle. So this is the same thing as inverse sine of negative sine 3 pi over 10. So because this is an odd function, we can pull out the minus and write this as negative of inverse sine 3 pi over 10. Was that any simpler? Well, yes. Now you can just write down minus 3 pi over 10 because sine of 3 pi over 10, inverse sine of that is cool. That's okay. When you're in the range minus pi over 2 to pi over 2, you're all good. The inverse sine of the sine is correct. So you have to be really careful. In case you think you've never seen anything like this before, this is exactly the same as saying the square root of minus 10 all squared is equal to, well, it's not minus 10, is it? Because the square root's always positive. It cannot be minus 10. Instead, that's the same thing as the square root of 10 squared, which is 10. So I'm sort of doing a similar idea. I'm replacing minus 10 by 10. Here I'm replacing this 13 pi over 10, the sine of that, with the minus sine of 3 pi over 10. And just to make matters really, really interesting, if you change these things to cosines, so inverse cosine of cosine is something altogether different. It's in the book, as I said, 10.2.6, it turns out to be 7 pi over 10. But if you do it with 10, it turns out to be 3 pi over 10 all along. So you can't guess what these things are, and I do think you should check that out. The one other example that I just want to give really, really quickly, and then I've got to move on to linearization. What if you do it in the other way? What if you take the sine of the inverse sine? Well, first of all, this number had better be between minus 1 and 1, or else you're not allowed to take the inverse sine. The domain of inverse sine is minus 1 to 1. So that's okay. Well, this version is easy. Inverse sine is between minus pi over 2 and pi over 2. So it's just in the fourth quadrant or the first quadrant. Sine must be whatever the original one is. So actually, sine of inverse sine is always going to be the same as the original. It's when you do the inverse sine of the sine that things get tricky. Okay, so please do check out that section. All right. Well, that's all I want to say about inverse functions. Any questions? Not problems yet. Problems are coming in half an hour. But I do want to spend the last half hour on linearization. So actually, has anyone covered any linearization in class yet? So guess what? I'm actually ahead of the class. Well, it is supposed to be a review session, not a preview session, but I have half an hour to spare, and I seem to have fallen a little bit behind before, so I'm going to seize this opportunity to get a little bit ahead and give you a preview of linearization. What the hey? So change course, skip ahead to 13.2, it's halfway through chapter 13 in my book, and let's talk about linearization. Now, this is a beautiful topic. It's very straightforward, self-contained, and it only has one idea in it, but it's very useful. And also, it's the beginning of something called Taylor series, which is a Math 104 topic in the second half of Calculus Lifesaver, if you happen to be holding that in your hands. So in any case, though, this is the sort of simple version of it, and it's already quite useful. So here's an example of a problem that I might ask you if I was feeling sadistic. Tell me everything you can tell me about the square root of 11. What is it? I want a ballpark of what it is. Well, who wants to take a stab at it? Without a calculator, what do you think? Yeah, it's between 3 and 4. Maybe closer to 3, because 11's closer to 9 than it is to 16. So I want to think of this as 3 and a bit. Okay, so without using a calculator, can anyone tell me what the bit might be? I don't expect an answer here because I don't know. We're going to use a bit of calculus to find out what it is. Here's the strategy. First of all, let's draw a picture. I'm interested in taking square roots. So let's just take y equals square root of x. See, there's no function here. I just started off with root 11. I'm going to introduce a function. Y is square root of x. If you go up to this height, that is the square root of 11. Now, why do we say it's 3 and a bit? Well, because you knew that 9 is a little bit less than 11, and the square root is pretty nice at 9. So let's draw that in. Square root of 9, of course, is 3. Now, I'm going to use green. Suppose we draw the tangent. At this point, at 9, 3. I'm drawing the tangent there because I kind of know what's going on at 9. Square root is nice there. Suppose I plug in 11 to this tangent line. I get that height. I didn't draw this to scale. It turns out these are actually quite close to each other. These are quite close to each other. You see, here, the line and the curve actually touch. The green line, the tangent, touches the original curve. So it's bloody close when you're near 9. The nearer you are to 9, the closer it is. And at 9, it's perfectly close. It's the same. So even though you've gone a little bit further to 11, it's still fairly close. In fact, you know, the true graph of root x, I should have drawn it a lot closer. And I think the graph that I have in my book is closer, but I knew you couldn't see the difference out there, so I've exaggerated it. Anyway, we're going to use this as our approximation. That's why I don't use green. Okay, so we need this line, y equals L of x, is the green line, and the approximation is L of 11, right? Because if I plug in 11 into the y equals L of x, then the height is L of 11. This is the approximation. All right, so let's find it. We need the tangent line. Well, we know how to do this. We need the tangent to y equals root x at 9, 3. Well, let's find it. First of all, we have dy dx is 1 over 2 root x. So when x equals 9, dy dx is 1 over 2 root 9, which is 1/6. So we are looking for a line of slope 1/6 through 9, 3. That's it. This is the line, slope 1/6 through 9, 3. So its equation is y minus the y coordinate 3 is the slope times x minus the x coordinate 9. And if you work this out, you get y is 1/6 x plus 3/2. That's how it simplifies. Okay, I need a little bit more of room. Any questions about that? Okay, never mind. I'm not going to yodel. Not enough stuff on the board anyway. Maybe later after the tape has stopped rolling. Okay, so I have found the equation of the line, and I'm going to now call it L of x is equal to 1/6 x plus 3/2. That's the equation of that green line in the picture before. Okay, so now here is the key idea. As I said, we are going to approximate f of x to L of x. I'm going to pretend that the curve is the line, at least when x is near 9. Right? If we come back over to this picture, when x is sort of in the vicinity of 9, the green and the white are pretty close. Not over here. Over here, they're terrible. This is at 3/2 and this is down at 0. Terrible. But nearby, it's good. Okay? Now, when x equals 9, they're both 3. They're both 3. Plug it in. You get, remember, this is root x, and this is 1/6 x plus 3/2. Plug in 9 if you don't believe me. You get 3 there, and there you get 9/6, which is 3/2 plus 3/2, which is 3. So at 9, they're equal. Near 9, they're almost equal. So in particular, 11 is somewhat close to 9. It's 1/6. And if you work this out, you get 11/6 plus 9/6, which is 26, which is 10/3, which is 3 1/3. So what's root 11? 3 and a bit. What's the bit? It's about 1/3. Well, it's more than we knew before. And we didn't even need a calculator. Okay, now this is not the general method. I'll give you a formula for it, but the general method is nothing other than what we've done. Okay? That's how you're going to approximate things. Before I do the general method, let's just come back over here. Just look at the picture. This approximation equals now 3 1/3. We found that. So is this an overestimate or an underestimate? It's an overestimate. It's an overestimate in this particular case. The reason being that the green line was above the curve. The curve was pointing concave down. We haven't actually done concave yet, up or down. And to tell you the truth, that very reason is why I postponed this to chapter 13 after we do concave up and down in the book. So I just didn't know how to put it there. It makes more sense to me to do it later, but that's how it's appeared in the syllabus. I guess that's how it is in the text, so no problem. As long as we understand that this thing is sort of facing down, if it was facing up like this, then we would get an underestimate instead of an overestimate. Okay, very good. So, hey, we've done a lot. We've done a lot. Now we just need to generalize it. So let's do it. In general, our picture looks like this. Instead of 9, I'm going to take some point that I'll call A. And here's my function, y equals f of x. And I'm looking for approximate values of it near A. I'm going to assume that I know exactly what's going on at A. That's the sort of known anchor point, if you like. And instead, I'm going to use the linearization here. To approximate f. And I need the equation of the linearization. So let's just work it out in general. What I get is, so I want the line tangent to y equals f of x through a f of a. That's the point on the curve, a comma f of a. And I want that tangent line. Well, the slope, of course, is f prime of a. So actually, the equation is fairly straightforward. It's y minus f of a is equal to, so y minus the y coordinate here, is the slope f prime of a times x minus the x coordinate. And if you make y, if you solve for y, I'll put the constant first. You get that formula, but of course y is equal to L of x. So there's the formula that generalizes this formula 1/6 x plus 3/2 from before. This is now a general formula, and it looks like this. I'm just going to rewrite it. And that is the tangent line at x equals a. But because we don't like to use two words, short words like tangent line, where we can use one long word like linearization, we will also call it the linearization at x equals a. Okay, the reason it's called linearization is it's supposed to be evocative, that you are taking this curve and you are sort of hammering it out into a line. And it's the best possible line you can use, at least if your center is at A. If that's the focus, then that is the best possible line you can use. So actually, the full formula I want you to learn, we are assuming also that f of x is approximately equal to L of x when x is near A. And remember, it's perfect when x equals A. But near A, this is good. So I'm just going to combine these formulas for something for you to learn. But I do want you to understand where it comes from. There's the formula with the understanding that approximation valid for x near A. Now, of course, how near depends on how rapidly the function changes. I guess you could come up with a really spiffy function that did this. Right? Something like this. And then the tangent line would be like this. And it's quite a good approximation when you're really, really near. But it's lousy over here and over here. So near is a relative term. It depends on the actual function. But if your function is kind of nice, doesn't veer around too sharply, then that's a pretty good approximation. So remember, again, we are using the tangent line instead of the function to have an approximation. Okay, so let's just redo the problem that we did before with that formula so we can see that we don't have to redo everything from scratch. And I'll show you how easy it is with the formula. Then I'll do a couple more examples. And then that might be it. I still have 15 minutes. Maybe I'll talk about the differential for a few minutes and wrap up the topic more or less. I am going to have to continue it a little bit at the beginning next time, because there's one more aspect to it that I definitely won't have time to talk about. But in any case, so to estimate root 11, okay, if that was the original problem, once again, without actually drawing a graph, I'm just going to apply this formula here. Now, if you actually look at this formula, actually, I'll just write it out again, because we're going to need it. F of x is approximately L of x, which is equal to f of a plus f prime of a, x minus a. It's quite clear that you need a function to start off with. Now, no one is going to pick it for you. You have to look at root 11 and say, I think I need f of x equals square root of x. Why? Because I'm taking the square root of something. Now, if I could just take root 11, I'd be done, but I can't. I need a point near 11, which is a candidate for the number a. Actually, let me leave one little line of room here. What is a? You know what? I'm going to even put it above. I need a number near 11 that I can nicely take the square root of. Well, we've already discussed it. It's 9. So the derivative is 1 over 2 root x. And the derivative at 9 is 1 over 2 root 9, which is 1/6. That's just nice working to keep this tidy. You see, f of a is just square root of 9. Oh, I could even put this over here first. F of 9, f of a equals root 9 equals 3. So this is 3 plus the derivative 1/6 times x minus 9. And actually, even though before I wrote it as 1/6 x plus 3 halves, I kind of like this form better. I like it unsimplified, because this really shows you that it's 3 and a bit. Right? It sort of isolates the bit, as it were. So in particular, the square root of 11 is just f of 11, which is approximately L of 11. That's the green line, which is 3 plus 1/6 times 11 minus 9. And now you can clearly see it as 3 plus 2/6, or 3 plus 1/3. So I've written it like that to be 3 and a bit. Okay? Actually, this is probably as good as any time to give you a notation for this bit. It's called df. It's the differential. It's the bit. It's called df. It's not df d anything. It's just df. It's a shorthand for f prime of a x minus a, the bit that you have to add on to the original value, f of a, in order to get the approximation to the value that you care about. I'm not saying that it's the same as delta f. Delta f would be this number minus 3. It would be actually the square root of 11 minus 3. But instead, the differential is just 1/3. That's the actual df at 11. It's the amount that we add on to get our approximate value. Okay? So, by the way, this approximation is not just good for 11. We can take any number that is close to 9. If we repeat the dose with 8, you get 3 plus 1/6, 8 minus 9, which is 3 minus 1/6. Or if you prefer, 2 and 5/6. But this is also evocative. The square root of 8, of course, is a little less than 3. How much less? About 1/6. Not so bad. Not so bad. Again, it's an overestimate because the curve that we want is always below that tangent line. So the curve looks like this. What if you did something sort of silly? Like, what's the silly example? Root 62. Well, suppose you try to use this. You get f of 62. That's the square root of 62. It's approximately 3 plus 1/6 of 62 minus 9. And if you work that out, you get what? 62 minus 9 is 53. And that's actually a little less than 9, so this is 11 and 5/6. So according to this formula, the square root of 62 is about 11 5/6. What is the square root of 62 properly? Well, what's the square root of 64? So the square root of 62 is a little under 8. Yuck. Should be 8, should be 7 and something. So what went wrong? Yeah, 62 is too far away from 9. The curve, root x, starts really curving down, and the line just keeps going on. So the further you go, the worse it's going to get. And this is already too far to be of use. So these are only approximations here. But if you think about it, how does your calculator even do the approximation? It actually has a clever algorithm for root x, but for a lot of these sort of weird functions, your calculator is basically doing something like this. There's a snazzier method where you don't just use the tangent line, but you use tangent quadratics and tangent cubics. That's called Taylor series. But for the moment, the tangent line is pretty good. So how would you do the square root of root 62? This is bad. How would you do it? Yeah, you repeat the problem, but instead take a equals 64 in the first place. And so now if you work it out, f of a is 8, f prime of a is 1 over 2 root 64, which is 1/16. And so here, f of x is approximately L of x, which is f of a, well, maybe I better write it out, plus f prime of a, x minus a. But here a equals 64. So if you work this out, this is 8 plus 1/16 x minus 64. And that's near 64. For x near 64. Okay, so in particular, square root of 62 is approximately L of 62, which is 8 plus 1/16, 62 minus 64. This is minus 2, so it's 8 minus an eighth, or 7 7/8. That's more like it. Okay, so you've got to make your linearization tempered with or depend on where you're going to be. All right, so let's look at a few more examples. Well, try this one. Estimate sine of 11 pi over 30. Okay, by the way, this is in 13.2.3. Okay, well, it's the same sort of problem, but different function, different points. What's a number close to 11 pi over 30 that you can easily take the sine off? Yeah, 10 pi over 30 is pretty close to 11 pi over 30. If the problem was estimate sine 10 pi over 30, you'd say, oh, 10 pi over 30, that's just pi over 3. I know what sine pi over 3 is, and you just write down the answer. There's no need to estimate. You know what the exact answer is. So, what should the function be? What are we actually doing? Well, we're taking the sine. So let f of x be sine x. Again, no one is going to do this for you. You have to do it yourself. You need to pick the function. Calculus is about functions. I've said it before. I'll say it again. And if you just have estimate this, you're not going to do any calculus unless you have some sort of function and a variable. Now we need this point A to be close 10 pi over 30, or otherwise pi over 3. So f of A is sine pi over 3. And what is sine pi over 3? Do we know? We should know. Come on. Sine pi over 3. Root 3 over 2. Good. What is the derivative of f? Well, it's just sine, the derivative of cosine. So what is the derivative at A? Well, it's cosine pi over 3, which is cosine pi over 3, 1/2. Okay, so the function value is root 3 over 2, and the derivative is 1/2. So we immediately write f of x, which after all is sine x, mightn't hurt to write that down, is approximately L of x, which is f of a plus f prime of a, x minus a. Look familiar? That's the general formula. So in this case, f of a is sine of pi over 3, so it's root 3 over 2 plus the derivative 1/2 x minus a. And, well, sine x is approximately equal to that. Okay, I just want to revisit this in the context. If x is actually equal to pi over 3, this equation just says sine pi over 3 is approximately root 3 over 2. Well, of course, it's perfect. You don't even need the approximate. This is the differential. It tells you how much away you are from root 3 over 2 when x is close to pi over 3, but not actually equal to it. So this is all good when x is near pi over 3. So this says that sine of 11 pi over 30, which is what we actually want to estimate, is approximately equal to, by the way, you have 1 equals here, you have equals, equals, but there's one important approximate equals, and that makes everything here approximate to everything there. Unfortunately, equals, 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 approximately equals, equals, equals is not just, the approximate does not get washed out. It trumps all of them. Anyway, you get root 3 over 2 plus 1/2 11 pi over 30 minus pi over 3. And if you work this out, that's 11 pi over 30 minus 10 pi over 30, so it's just pi over 30. 1 pi over 30. That makes it a pi over 60. And you get root 3 over 2 plus pi over 60. Now you might quarrel, no, that's not the word, quibble. I don't know, you might point out that these are still not obvious quantities. And yet, root 3 is not so hard to estimate. In fact, you could even use the linearization sort of stuff we did before. We know pi is about 3.1415. I mean, these things are constants that once upon you work this out for once and for all, and you can get good approximate decimal values of this. But the original thing is really messy. I don't know how you do that. What are you going to do? Draw a triangle, take a protractor, and try to measure out 11 pi over 30 in radians, and then estimate this length over this length? Ugh. So even though the answer is not a lovely fraction, it's at least something we can get we can get a handle on it. We know what it's about. That's about 1.7. That's about 3.1. I could use those approximations and already get a better idea than what I would have had before just looking like this if I didn't have a calculator. Obviously, if you have a calculator, everything changes. But again, this is a pretty important area of math, and besides, how do you think they make the calculators in the first place? Someone needed to know this. So, in any case, I think that's just about it. I still have 2 minutes, but I am going to stop there. Thank you.